Okay, inverse trigonometric functions. You've used inverse trigonometric functions before. You used them in year 9, year 10 and year 11 without necessarily realising that you were. But let's get cracking with them and I'll show you where you've used them before. So an inverse trigonometric function has been used with, say, standard SOHCAHTOA trig. So for example, you might not know that this is theta. You might know that's 11 over 8. And so in this case, you've got the adjacent over the hypotenuse. Cos of theta is equal to 8 over 11. Okay, and then what you would have used is theta is equal to cos to the negative 1 of 8 over 11. Okay, that there is inverse trig. Okay, that's the inverse of cos. Now that is sometimes called cos to negative 1 of x. It's the one that you'll be most familiar with, but it's also sometimes called arc cos of x. Sine's got the same one, tan's got the same one, so sine to negative 1 of x equals arc sine of x, tan to negative 1 of x is equal to arc tan of x. They're just two different ways of writing the exact same thing. Please don't let that put you off. Okay, we should know that when you've got a function to the negative 1, you've got an inverse of the function. Arc is just a different way of writing it. So we need to remember some stuff about functions before we started. So this here, straight line, that is a function. Great, okay. It's a 1-to-1 function. Okay, it maps 1-to-1. So you put in one thing, you get out one thing, and for every one thing that you get out, you know exactly one thing that went in for it. Okay. A quadratic like that. Okay. There are many different ways to get the exact same one solution. Okay, if we go across like that there. Okay, and so that there is a many-to-one function. Okay, it is a function. It's a many-to-one function. When you find the inverse of it, though, you'd be finding a one-to-many, which isn't a function. The inverse of this would look something like that. That's not a function. The reason is that I can put something in and I don't know what's going to come out. It's no good doing that. Okay, it's no good putting in all the ingredients to make a loaf of bread and out comes, you know, a pair of shoes. You just don't know what's going to come out of it. And so that's not a function. And so you'll see if you ever try to graph, say, y equals the root of x on GeoGebra, y equals root of x looks something like that. Okay, because it's been defined obviously only in this region here, so that you don't get some sort of non-function. Okay, so many-to-one is absolutely fine as a function. There are many different ways to get the same one solution. That's fine because you know that one solution that you're going to get. One-to-many is not okay as a function. Now, when you're dealing with functions and their inverses, you should only be using one-to-one, because if you've got one-to-one as the original function, then the inverse of it will be one-to-one, and so both of those work. When you've got many-to-one as an original, that works, okay? There are many different ways to get the same one solution out. I only really care the fact that I know what one solution I'm going to get out. But the inverse of it would be one-to-many, which doesn't work. Okay, that's no longer a function. And so what we'll end up doing is we need to restrict the domain on the original in order to produce an inverse that is actually still a function. Okay? The rule is stick to one-to-one, and you'll be absolutely fine. So let's get cracking with having a look at some of these graphs. So arc sine of x. So with arc sine of x, I'm going to first off just do a quick sketch of what sine looks like. Well, sine looks like that, doesn't it? Okay, I'm going to go back a little bit as well. You'll see why in just a second. And that there is a many-to-one. Okay, there are many different ways to get the same one solution out. There are two different ways. If you carried it on, there'd be infinite different ways. Okay. I need the region that's going to make it one-to-one, so that when I use the inverse of it, I'll get a one-to-one. If I used a one-to-many, finding the inverse would give me a many-to-one. There'd be many different. If I used a many-to-one, which is what I've got here, if I found the inverse, I'd get a one-to-many. So there'd be one thing going in and many different things coming out. So we have absolutely no idea what's going to come out. So I need the region that's just one-to-one. And in actual fact, that is here to here. Okay, those aren't asymptotes or anything like that. It's just I didn't want to draw a thick line because it might look like an axis. I need that bit there. Okay, there are 3 important coordinates in there. It's a good idea to get those coordinates written down. Okay, I'm going to deal with degrees. This is 90 and 1. 90 in, 1 up. This one's obviously the origin, 0, 0. Okay, and this one is negative 90, negative 1. Negative 90, negative 1. So, let's have some axes. So first off, I've got 0, 0, that's obvious. That one's already done. 90 and 1. When I inverse that, I'll go in 1 and up 90. Okay, into 1 and up to 90. Just going to take me up there. Okay, with this one, I'm going to go into negative 1 and down to negative 90. Okay, so there's negative 1 and here's negative 90. There's my bit there. Okay, those are the three coordinates all inverse. What you can see is also the axes, values on the axes inverse. So we were starting going from 1 to negative 1 where it, on the horizontal where it would have previously been on the vertical. Look here as well. The lump goes out like that. We should know from functions earlier on this year and last year that you reflect it over y equals x. Okay, you reflect it sort of thing there like that. Okay, in this case it's actually reflecting over something a little bit different because it's related to those, but it sort of has the same sort of look to it, but it looks like that there. Okay, that there is the graph of y equals arc sine of x. Okay, its domain is from negative 1 to 1, its range is from negative 90 up to 90, it's all equals to, so they're allowed to be equal to it. But there you go. Okay, there's the arc sine of x, and we're going to be returning to that quite a bit throughout this lesson. Arc cos of x. So arc cos of x, again, let's take a look at the region that I actually care about for this one. So arc cos goes, cos of x goes down and up like that. Okay, and down and up like that. Obviously, you should be drawing a bit of a better picture than me. Now, I cannot have this region as well as this region. I can't have it because if I do, there's a turn back there. And as soon as the function turns back on itself, it's allowed to do it in the original, but in the inverse it won't be able to do that because it'll be turning back on itself like that. Okay, be absolutely no good at all to anybody, and so I can't have that region. I want this one, and I want the maximum amount for the range that I can get, because that'll give me the maximum amount for the domain in the inverse. And so I want that one, and I want that one. Okay, but I don't want that bit because it's turning back, and obviously that bit's matching against that bit, so it's no good at all. So I want these ones, this bit here. The coordinates of those are 0, 1. They are 90 and 0. And this one is 180 and negative 1. So let's have a go at drawing arc cos of x. Well, first off, we've got, instead of it being 0 in and 1 up, we're going to go 1 in and 0 up. That's that one. Next, instead of it being 90 in and 0 up, we're going to go 0 in and 90 up. There's 90. Okay, and on this one, instead of it being 180 in and negative 1 up, we're going to go negative 1 in and 180 up. Should be up there, like that. There you go. Okay, the arc cos function looks like that. Okay, again, you could write down your domains and your ranges and whatever else, but the critical thing is to notice that that there is 1 to 1. Okay, it's really important to notice that. Okay, arctan. Well, the region of tan that is 1 to 1 is this bit. Okay, from negative 90 up to 90, goes like that. All right, where that's 0, 0, obviously. Where that asymptote is at 90 degrees and that asymptote is at negative 90 degrees. Okay, when you draw an arctan, the asymptotes will go from being vertical to being horizontal, and so you've got, instead of it being vertically at 90, it's going to be horizontally at 90 degrees, and instead of it being vertically at negative 90, it's going to be horizontal at negative 90 degrees, and you're going to end up with that and that. There you go, there's arctan. Okay, moving on. These are no-calc questions. Normally you just tap it straight into a calculator, there wouldn't be much of an issue with it, but you know, you could be asked not to use a calculator, but it's pretty rare that you're going to be asked that. These things here, it's pretty handy to have the magic triangles written out. I've made them all pretty much out of the same triangle though, so that's 60, that's 30, obviously that's also pi over 6, isn't it? And that's pi over 3. where that's 1 and 2 and root 3. You have to know these. They're really important. You need to know these. So we've got arc sine of root 3 over 2. So first off, arc sine, so sine to negative 1 of root 3 over 2 is equal to, I'm going to give it some value a, because it gives me an ability to manipulate it a little bit. What I'm going to do is I'm going to apply sine to it. Sine of sine to negative 1 of root 3 over 2 is equal to sine of a. Now, sine of sine to the negative 1, those two things, one of them is the inverse of each other. Okay, and so when that happens, they'll undo. So imagine you had x goes in, you multiply by 3, and then you divide by 3, you get out x. Okay, if I put in 1133, it gives me back 11. Now that is because multiplying by 3 and dividing by 3 are inverses of each other. The same sort of thing goes with sine and inverse sine. You plug it in, you apply sine to it, you apply inverse sine to it, and you get back out whatever you plugged in. You need to be careful with it though, because arc sine's obviously it's only got certain parts where it's actually defined. You saw that on the graph, and we'll have a look at it in a sec. For now though, you should know that sine of sine to the negative 1, that just sort of disappears, sort of thing. So you're going to end up with root 3 over 2 equals sine of a. Okay, sine of some value is going to equal root 3 over 2. Well, root 3 over 2, that is the opposite over the hypotenuse in this case. Okay, so there's the opposite over the hypotenuse. Sine of 60 equals root 3 over 2, doesn't it? We know that. We know that sine of 60 equals root 3 over 2. And so by comparison, you can see that a must equal 60. Okay, I should have done that, all of that in radians, which would be pi over 3, obviously. You're welcome to work in degrees and then switch back to radians. It's my mistake. I should have just read it more carefully because I did it in degrees like a big wally. Okay, moving on. Oops. We've got question B. Question B is very similar, but not identical. Okay, it's got this, and this is really, really critical. Let's take a look back at the sine graph, the arc sine graph, sorry. Now, the arc sine graph is only defined from negative 90 to 90, okay? We can only use negative 90 up to 90 if we're going to be using arc sine. Now, when we look at that in terms of cast, it means that we can only be using negative 90 up to 90. We can only be using those. So we can't use that one and we can't use that one. Some of you might have looked at this and gone, well, if that's 60, then surely I can also use 120. Well, no, not really, because you're using arc sine. And arc sine doesn't go up to 120, it only goes up to 90. Okay, so we can only be using these ones. Now this negative one here is going to fall into that region there. Okay, and so in this case, if this was pi over 3, this one would be negative pi over 3. You can use the graph for it if you want to as well, which is really nice. You can mess around with the graph to work that out. But I think you should sort of investigate that yourself. So it's not overly complicated, to be fair. Next, we've got arctan of negative root 3. So arctan of negative root 3 in degrees. I'm going to do this on the tan page, why not? So we've got arctan of negative root 3 in degrees. And this is going to give you a bit of a clue about that thing I said that you could do with the graph, because I'll show you how to deal with the graphs with this stuff as well. The first thing I'm going to do is I'm going to ignore the negative. I'm not overly interested in that. I'm going to say, well, arctan of root 3 equals C. I'll work with this first, okay? And then I'll figure out, in fact, I'll call it D, shall I? And then I'll work out C in just a second. So, tan of arctan, that'll disappear, won't it? Tan of arctan, we'll end up with root 3 equals tan of D. Okay, so we were working in degrees, it asked for in this case, which is a treat. There we go, 1, 2, root 3. Toa, opposite over adjacent. It's not that one. Opposite over adjacent. So tan of 60 also equals root 3. Root 3 equals tan of 60, doesn't it? And so therefore D equals 60. Now that's great, that's fine. Okay, so if we plug in root 3 Okay, so that's root 3 there. When we plug in root 3, we get out 60 like that. Okay, now using the graph to work out negative root 3 being plugged in, it's pretty obvious that that should be negative 60. Okay, so C equals negative 60. The trick here is to try to use the positives so you can get used to using your magic triangles for it. And then once you use your magic triangles, sort of use the graph to work out the remaining bits. It's not overly complicated. Should be absolutely fine with it. Okay, next we've got cut of arc cos of 0.5. Not overly complicated, but we will need our magic triangles for it. So obviously you could normally just type this into your calculator, but I'm going to show you how to do it without. We've got 30 and 60, and we've got 1 and 2, we've got root 3. Arc cos of 0.5, obviously that's 1/2. And so you've got the adjacent over the hypotenuse. Okay. So what I know is that if I've got cos to the negative 1 of 0.5, okay, I'm going to try to work out that that's going to be called A, some value. Don't know just yet what it is. Well, now I know that 0.5 is equal to cos of A. Okay, so cos of some angle is going to equal 0.5. Remember, the thing that goes with cos and sine and tan is always going to be the angles. This is always going to be cos to the negative 1, sine to the negative 1, and tan to the negative 1 is always going to be next to the ratio of the sides. And so what we've got is cos of some angle equals 0.5. Well, that angle's got to be 60. Okay, so A must equal 60 because you've got the adjacent over the hypotenuse, and so therefore A equals 60 degrees. Okay, so we now know that cos to the negative 1 of 0.5 is equal to A. Well, A equals 60, so actually what I'm working out is going to be cot of 60. Okay, well, cot of 60 is 1 over tan of 60. Okay, so let's work out tan of 60. Well, toa, opposite over adjacent, toa. Okay, so you've got root 3 over 1. Tan of 60 is equal to root 3. So therefore cot of 60 must equal 1 over root 3. Now if cot of 60 equals 1 over root 3, that's the answer to this, but we could also rationalise the denominator. We can end up with root 3 over 3. Okay, and so that thing comes out as root 3 over 3. Alright, next up. Given that arc sine of k equals alpha, where k is between negative 1 and 0, in other words it's sort of in the negative bits, and alpha is in degrees, it's supposed to say alpha but I can only find an A, is in degrees and is greater than 0. Find the first two values satisfying sine of x equals k. Well, if sine of x equals k, x equals k, and also sine to the negative 1 of k equals alpha, we'll deal with all these restrictions in just a minute. We've got sine to the negative 1 of sine of x is equal to alpha, and so therefore x must equal alpha. Okay. Now we know that alpha has got to be greater than 0. We know it's going to be in degrees. That's fine. But we also know that sine of the value of x is going to be less than 0. Okay, so let's take a look at the original sine graph for this. So the sine graph for this starts off up like that, down like that, okay, where this is the value of x that's going in, and coming out is the value of k. Okay, and we want the region where k is between negative 1 and 0, so it's going to be in here somewhere, isn't it? Okay, k has got to be in there somewhere, in that sort of area. Okay. Now we don't know what it is. It's obviously totally general. There's no actual numbers in it apart from just there. Okay, and so we're going to call that there the value of k. Now the value that produces that, we already found out that it was when x equals alpha. Okay, when x equals alpha, we get out a value of k. All right, but it wants the first two values that does that. Okay, it's greater than 0 for alpha, so it can't be over here somewhere. Okay, it's got to be over on the right hand side. And so the next time that it will be produced will be here. Okay. Now here, if we're in degrees, this is 360. Okay. And so if that gap there is alpha, is 180 plus alpha, okay, then we've got this gap here that we need to try to work out, okay, which is a little bit of a weird one, but let's have a little look at it. Okay, so if this is alpha going in, okay, alpha, we could say, well, alpha is made up of 180 plus some of a little bit there, okay. I'm going to call that little bit B, okay, beta if you want to. Okay, so we've got that. Alpha is equal to that thing. So what I need to find out is what's this gap here? Well, this gap here would be 360 minus that value, beta. Okay, but beta is equal to alpha minus 180. And so therefore we've got 360 minus alpha minus 180. Okay, and so therefore you get 360 minus alpha plus 180, which equals 540 minus alpha. Okay, it's actually a little bit more obvious than you'd think, really. If you think about 540 would be up there, okay, then this gap would be 180 and alpha away. This gap would be 180 and alpha away from 0, but that one's from 540. You just got to be really careful with that. Don't think that it's 360 minus alpha, because it's not. Alpha's actually over 180. It's quite big. There's a book question that you're going to get in the exercise that's not like that. It's a lot simpler, but I just wanted to show you something that looks like that because it's interesting. All right, moving on. F of x equals arc cos of x, where x is equal, x is within that. We sort of knew that it was going to be. That's fine. G of x is equal to f of 4x. Weird. Okay, we're working in degrees. So we're going to first off sketch y equals f of x state in the domain and the range. Okay. Well, we should know what arc cos was looking like. Okay. We can have a little look back if we want to. Arc cos was that one. Okay, from -1 to 1 across and then up to 180. And so I'm just going to cheat and I'm going to take that one there. Okay, which was from 1, -1. Okay, we had 90 and we had 180. And we had that there. Okay, there, that is f of x, where you've got the domain for x being from -1 to 1, which we knew anyway, that was given. Okay, but the range is from 0 to 180 degrees. Okay, that's the domain and that's the range. It's handy, we might use that in a bit, but we'll see. So for B, we have f of 4x, okay? Well, that looks like it's going to multiply your x's by 4, but we know that it doesn't, okay? We should know that it won't do that, okay? It will take your x's and it will squeeze them in, okay? It will squeeze them right in, because you only need a quarter as much to produce the same result. So we've got this thing here, okay? It would be really, really, really squeezed in versus that one, and the normal thing to do would be to try to kind of draw it like underneath just in case you needed it. I'll do that, but you don't always have to. 1/4 and -1/4. We've got 90 and we've got 180, and so we've got that there. That's our sketch of that, okay, where x can be between -1/4 and 1/4. That's fine, and there's no change in the range, okay? So g of x can be up to 180 degrees and down to 0 degrees. All right, define g of x without the use of the function f. Okay, well, this is actually really easy, because if g of x equals f of 4x, but f is equal to arc cos of x, well then g of x will be equal to arc cos of 4x. Okay, that there is that graph. Okay, you could call it cos of -1 if you wanted to. Next, define the inverse of g of x. So the inverse of this. All right, finding the inverses, we're going to have y equals cos to -1. Remember, whenever you find an inverse of a function, change the function to a y, change the subject to get your form. Okay, so I'm going to do that. I'm going to get cos y equals 4 over x. 1/4 cos y is equal to x. There's my form. Now that I've got my form, I'm going to use the form to give me the function. Okay, well, the function should be the inverse of g, so that's going to be g to the negative 1 of x is going to equal, this is my g to the negative 1, this stuff. This is still a function of x, and so this needs to be an x here, okay? And so we're going to end up with 1/4 of cos of x, okay? Stating the domain in the range. Now, the domain in the range for this will be the opposite of that, okay? So your domain for x will be from 0 to 180, okay? The range of the original will be the domain of the inverse, okay? So x will be from 0 to 180 degrees, okay? And the range will be where g to negative 1, its range will be from 1/4 and negative 1/4 with a lower bit. All right, easy peasy, moving on. Your tasks, Edexcel Year 2 book, you know where it is, page 160, exercise 6E. I'd like you to have a go at questions 3, 4, 5, 7 and 8, okay? Some of them are blindingly obvious, like the things with the sine and the arc sine thing. You can have a go at trying the magic triangles out, but you should be just getting a little bit of practice with those. And some of them are a little bit more tricky. You will need to probably re-watch this video, have a go at it, mark your questions, tick them and upload them to Google Classroom. Cheers.